بسم الله رب اشرح لي صدري ويسر لي أمري واحلل عقدة من لساني يفقه قولي. Welcome to this video blog. This is a reproduction of my defense of a mathematical proof for the course MAT-470 Real Analysis, and this is for the Southern New Hampshire University. Welcome to this video blog. In this presentation I want to explain the tie between differentiability and continuity, and therefore the mathematical problem to be proved would be related to this. So before I go through the mathematical problem, I will first give a quick revision of the concepts and notations used. I will follow it with the definitions and theorems that's going to be used in the mathematical proof. And then the main focal point of this defense or this presentation will be about mathematical proof. In the original defense, there was a session for questions and answers, and therefore you will find this point in this overview slide. So what's the mathematical problem? The problem will be of three parts. First, we have a function which acts on an open interval from 0 to infinity. And we suppose that f function of x over y is equal to f of x minus f of y for all x and y in the open interval, and that f of 1 is equal to 0. All of this is given. We want to prove that if f is continuous on the open interval, it will be so if and only if f is continuous at 1. And then we also want to prove that f is differentiable on the open interval if and only if f is differentiable at 1. Lastly, we want to prove that if f is differentiable at 1, then f prime of x is equal to f prime of 1 over x for all x in that interval. So what are the concepts and notations? A quick refresh. Everyone knows from calculus course that derivative is the instantaneous rate of change of a function. And geometrically, this will be the slope of the tangent line at a point, as you can see in this graph. We have to note one important concept here. The tie between differentiability and continuity is one way. Continuity would not imply differentiability, but continuity is implied by differentiability. That is, if you have a function that is differentiable, it must be continuous. But not all continuous functions are differentiable. And a very good example for this, for that is the v-shaped absolute of x function. As you can see in this graph, the v-shaped function is a continuous one, but it is not differentiable at 0. So when we talk about differentiability and derivatives, what would that mean? What would a slope of a line at a point on a curve mean? How do we calculate that slope? The slope of the tangent line is equal to the limit as the secant changes when x approaches c. Now, an important point to note over here is that a derivative of a function, we used to take it in calculus as f prime of x. But when you say f prime of x, that would be the derivative of the function at the point x. So in fact, the derivative of a function is only f prime. So if you want to make a notation of the mathematical notation of a derivative of a function, you need only provide f prime without the bracketed x. So what are the definitions and theorems that will be used in this mathematical proof? First, the definition of a differentiable function at point c, and that would be the limit of f of x minus f of c over x minus c as x approaches c. And if this limit exists, then it is called the derivative of f at c or f prime of c. Then the second part of the definition says that if f is differentiable, then it is differentiable at every number in I, in the interval I. So next we come to a very important lemma, which is about continuity. So if you have an interval I, an open interval I, and the c a point in the interval, and the function f, then f is continuous at the point c if and only if the limit of that function as x approaches c exists and the limit would be equal to f of c. Now, lemma 2 is another form of the differentiable of the definition of differentiability, but in this case it takes the distance between c and x and replaces it with h. So when x approaches c, h would actually approach 0. Now, theorem 1 is the important part which connects differentiability with continuity, and it says that if you have a function f of an open interval I differentiable at point c in that interval, then f will be continuous at c. And if f is differentiable everywhere in that interval, then f is continuous everywhere on that interval. So let's start with the mathematical proof. Now this is the problem. We'll start with part 1. So we know that f is continuous, we want to prove that f is continuous on the open interval if and only if f is continuous at 1. So we let f, which is to be the function, and we know that the given is f of x over y is equal to f of x minus fy for all x and y in the open interval 0 to infinity, and we have given and we are given f of 1 is equal to 0. So to prove that f is continuous if and only on the open interval if and only if f is continuous at 1, we need to prove the right side and the left side of this claim. So first we'll start with the right side, and we suppose that f is continuous on the open interval 0 to infinity. So we know by the definition of continuity that if f is continuous on 0 to infinity, then it's continuous everywhere in that interval. And since 1 is in that interval, then f will be continuous at 1. Then we go to prove the left side of the statement. So we suppose that f is continuous at 1 first. If f is continuous at 1, then the limit of the function of x over y as x over y approaches 1 exists. And we know from continuity from lemma 1 that it should be equal to f of 1. And we know that f of 1 is equal to 0. So we know that the limit of f of x over y as x over y approaches 1 should be equal to 0. So we can do some algebraic substitutions and manipulation. First, I'm substituting f of x over y because we know it is given that it is f of x minus f of y. So then the limit would become the limit of the function f of x minus f of y as x over y approaches 1. And we know that the limit of f of x, that this should become as the limit of f of x as x over y approaches 1 minus the limit of f of y as x over y approaches 1, as you can see here. But you should note that the limit of f of y as x over y approaches 1 is actually f of y. Why is that? Because y is constant here and x is approaching y. So it will still be the value of the function at the point y. So it is f of y. So we have the limit of f of x as x approaches y minus f of y. And we said at the beginning that that limit is equal to 0. So then the limit of f of x as x approaches y will be equal to f of y. But that is actually the definition of continuity. And since y belongs to the open interval from 0 to infinity, then it means that you have a function that is continuous over y and over the whole of the interval. By lemma 1, f is continuous on 0 to infinity. So we come to part 2 of the proof. Part 2, we need to prove that f is differentiable on the open interval if and only if f is differentiable at 1. Again, as I said, we have all the given at the top. Now we need to prove the right side of it. So if we suppose that f is differentiable on the open interval, then by definition of differentiability, f should be differentiable at every point in that interval. Since 1 belongs to that interval, then by definition 1, part 2 of that definition of differentiability, it follows that f is differentiable at 1. So we come to the left side of the proof. We suppose that f is differentiable at 1. Then the following limit exists. F of x over y minus f of 1 over x over y minus 1 as x over y approaches 1. Now, if we do some substitution, we substitute f of x over y by f of x minus f of y, then we have that second, on the right hand, the middle term. Then we know that f of 1 is given to be equal to 0, and we have the last, or the right hand side of this equation, which is limit of f of x minus f of y over x over y minus 1 as x over y approaches 1. But again, x over y approaching 1 implies that x approaches y. And therefore, the limit will become f of x minus f of y over x over y minus 1 as x approaches y. But if we take 1 over y as common in the denominator, then the denominator will become as 1 over y into x minus y. And if we take 1 over y outside the limit, this becomes the right hand side, which is y times the limit as x approaches y of f of x minus f of y over x minus y. We can safely take y outside because y is considered the constant term here. So then if we let x equal y plus h, that is the distance between y and x is h, then the limit can be expressed as y times the limit of f of y plus h minus f of y over h as h approaches 0. But as we deduce that this exists, then by lemma 2, it follows that f is differentiable at y. When we know that y belongs to the open interval from 0 to infinity, then this means f is differentiable on the whole interval. That brings us to the last part of this problem. We want to prove that if f is differentiable at 1, then f prime of x is equal to f prime of 1 over x for all x in the open interval. Again, we have the given as shown, but we want to note one thing. F of x over y is equal to f of x minus f of y is the same thing as f of y over x equals to f of y minus f of x, because the term y over x or x over y, I mean the x and y's are dummy variables. So you can actually replace them or actually interchange them. And that's what I'm doing here. I'm interchanging it, and I want to have my main variable to be y rather than x. So we suppose f is differentiable at 1, because that's what is given. And by definition 1, part 1, then f prime of 1 should be equal to the limit of f of y over x minus f of 1 over y over x minus 1 as y over x approaches 1. We can then substitute the value of f of y over x as f of y minus f of x, as you can see in the middle term. And we can substitute also the y over x approaching 1 by y approaching x, as you can see in the middle term. We factor out 1 over x in the denominator, so it becomes 1 over x into y minus x. And then on the right hand side, we know that f of 1 is 0, so we remove it from there. So it becomes x multiplied by limit of f of y minus f of x over y minus x as y approaches x. And we know that this limit is what? Is f prime of x. This is by definition, this is f prime of x. So it is actually then x times f prime of x, because we have x times the limit is equal to x times f prime of x. But on the leftmost of that equation, it is actually f prime of 1. So we have f prime of 1 equals x f prime of x. And with small algebraic manipulation, f prime of x is equal to f prime of 1 over x for all x in the open interval. That's the end of the proof. Thank you for listening, and have a nice day.